Let's start with the basics of acid-base physiology, which is defined by the regulation of hydrogen ions. The pH in the blood at any time is determined by the concentration of hydrogen ions. The body aims to keep hydrogen concentration within a range of 35 to 45 nanomoles per liter. 40 nanomoles per liter is the equivalent of 0.00004 millimoles per liter. To put this into perspective, the hydrogen concentration is incredibly low compared to the concentration of our other ions. In fact, it is approximately 1/millionth of our sodium, potassium, and chloride concentrations, meaning it is very tightly regulated. 35 to 45 nanomoles per liter corresponds to a pH of 7.35 to 7.45. We use the term pH because it is a much easier way to communicate a very small concentration. However, because P represents the negative log, hydrogen concentrations and pH are inversely related. Therefore, a high pH is representative of lower hydrogen concentrations, and a low pH is representative of higher hydrogen concentrations. To reiterate, the pH varies inversely with a log of the concentration of hydrogen ions. So as the concentration of hydrogen ions increases, the pH drops. So why does pH matter anyways? We do know that at a low pH, or high acidity, free hydrogen ions can bind to proteins, causing them to lose function. The body uses other molecules, buffers, to bind up free hydrogens. Bicarbonate, represented here, is the most abundant buffer. You can think of it as hydrogen sponges soaking up excess hydrogen ions to prevent them from causing damage. Other buffers include our hemoglobin, bone, and phosphate. The body maintains a physiologic pH by regulating the balance between bicarbonate and hydrogen ions. An excess of bicarbonate ions results in the higher pH. When the pH of the plasma is above 7.45, it is referred to as an alkalemia. An excess of hydrogen ions results in a low pH. When the pH of the plasma gets below 7.35, it is referred to as an acidemia. So how does the body regulate the balance of hydrogen and bicarbonate ions? Various systems exist to buffer excess hydrogen ions in different fluid compartments of the body, represented here. We are going to focus on one of the primary buffering systems, bicarbonate. This system functions in the plasma and interstitium. To understand the bicarbonate buffer system, let's start with the Henderson-Hasselbalch equation. The pH of a solution is equal to a constant, pKa, plus the log of the concentration of a conjugate base over the concentration of the weak acid. Bicarbonate is a base whose weak acid is carbonic acid. Carbonic acid is formed from carbon dioxide dissolving in plasma, which rapidly dissociates into hydrogen ions and bicarbonate. Carbonic acid is transiently present in the blood before forming hydrogen ions and bicarbonate, as depicted here. In the Henderson-Hasselbalch equation, we substitute carbon dioxide for carbonic acid. The partial pressure of carbon dioxide is much more readily measured than carbonic acid. So, the acidity is determined by bicarbonate over carbon dioxide. An easy way to remember this is that the acidity A equals B bicarbonate over C carbon dioxide. In an upcoming module, we'll review the handling of bicarbonate by the kidneys. For now, recognize that bicarbonate is regulated by the kidneys and carbon dioxide is regulated by the lungs. To understand these concepts, imagine bicarbonate and carbon dioxide in balance in the extracellular space as pictured here. The equation below represents this balance. Imagine how excess of one or the other may shift this equation in one direction or the other. Now, let's imagine how this can change in pathologic conditions. In normal physiology, the lungs blow off carbon dioxide, which prevents it from building up and causing an imbalance in the pH. But in a COPD exacerbation, CO2 removal from the lungs is impaired, and carbon dioxide builds up in the plasma. As the carbon dioxide builds out, the buffering equation shifts to the right with excess CO2, and more hydrogen ions are formed. An increase in hydrogen ions decreases the pH, increasing acidity. A process causing the buildup of CO2 in the plasma decreases the pH and is referred to as a respiratory acidosis. Over time, the kidneys will compensate for the rise in CO2 by increasing the concentration of bicarbonate. This brings the pH back up towards normal. This process is referred to as metabolic compensation. In contrast, in hyperventilation, too much carbon dioxide is blown off by the lungs. As the carbon dioxide concentration drops in the plasma, the buffering equation moves to the left, which drives down the concentration of hydrogen ions. And a decrease in hydrogen ions drives up the pH. Any process that decreases the partial pressure of carbon dioxide and thereby increases the pH is a respiratory alkalosis. If a person has a respiratory alkalosis, the kidneys will compensate by decreasing the serum bicarbonate. This will compensate for the change in PCO2 and normalize the pH. This process is again referred to as compensation. Next, let's consider changes in bicarbonate. In diarrhea, bicarbonate is lost from the plasma via the gastrointestinal tract. As bicarbonate is lost, the buffering equation is shifted to the right, and hydrogen ions are formed, and subsequently the pH will decrease. Any process that decreases the concentration of bicarbonate is referred to as a metabolic acidosis. Note that bicarbonate loss can occur through the gastrointestinal tract or the kidneys. The lungs will compensate by blowing off CO2 to balance out the change in bicarbonate. This compensation can happen quickly, as the respiratory rate quickly increases. In contrast to diarrhea, vomiting involves loss of stomach acids, like hydrogen chloride. With the loss of each hydrogen ion, a bicarbonate is generated. Ordinarily, as the bicarbonate concentration increases, the buffering equation is shifted to the left, and the concentration of hydrogen ions drops, with a subsequent increase in pH. An increase of bicarbonate concentration and resultant increase in pH is termed a metabolic alkalosis. The lungs will try to compensate by holding onto CO2 through hypoventilation to balance out the increase in bicarbonate. This is again referred to respiratory compensation. You may have noticed the terms acidosis, acidemia, alkalosis, and alkalemia thrown around. Before we wrap up, let's clarify those terms. An acidemia refers to a condition where the pH is below 7.35 due to any pathologic process. An acidosis is any process, respiratory or metabolic, that decreases the pH. Similarly, an alkalemia describes the state where the plasma pH is above 7.45. An alkalosis is any process that drives up the pH, including respiratory and metabolic changes. Here is a review of the expected pH changes with each primary acid-base disorder. The bicarbonate concentration and carbon dioxide always change in the same direction. Note that in respiratory disorders, the carbon dioxide and the pH change in opposite directions. In metabolic disorders, the bicarbonate and the pH change in the same direction.